Hello and welcome to Think Tech, the podcast where we explore the fascinating world of technology and how it's shaping our lives. My name is Shivam and I'll be your host today. In today's podcast, we'll discuss about Apache Kafka, the popular distributed streaming platform. Apache Kafka has become a critical tool for modern data-driven organizations that need to process massive amounts of data in real time. Kafka was originally designed and conceived at LinkedIn and was then handed over to Apache Software Foundation, and it's now an Apache project. One of the most widely used tools for building scalable, fault-tolerant, and high-performing data pipelines. In this podcast, we'll cover everything you need to know about Apache Kafka, from its architectures and core concepts to its use cases and real-world applications. So whether you are a developer, a data engineer, or a technical decision maker, this podcast will help you with the knowledge and insights you need to get started with Kafka and take your data architecture to the next level. So sit back, relax, and let's get started on this journey into the world of Apache Kafka. So let us first start by understanding what Kafka is. So I opened the Confluent introduction page for Kafka, and Confluent describes Kafka as a distributed event streaming platform that publishes and subscribes to streams of events similar to a message queue or an enterprise messaging system, stores streams of event in a fault tolerant durable way, and processes streams of events as they occur. So essentially it's an distributed event streaming platform which works on a publisher subscriber model, where there can be multiple publishers who or producers who produce messages, send it to Kafka. Then Kafka acts as a fault tolerant durable storage for those messages until someone from consumer side reads that message and process that message as they want to. So that is the basic definition of Kafka. Kafka is different from what earlier messaging queue system were used to do. So Kafka is based on a pub-sub model, whereas in messaging queues, the entire architecture was a little different. Although today, what I feel is that most of these products are able to perform what Kafka is also able to perform. So the critical difference between these two tech stack or these two concepts have now blurred a lot, but initially when they were designed, there was a significant difference between a message queue and a publisher subscriber model. So let us understand what a message queue was, and then we'll see how it is different from a publisher subscriber paradigm. So message queues consist of a publishing service, and there can be multiple consumers that communicate via a queue. So the main or the most important point about a message queue is that as soon as a consumer consumes a message, that message no longer exists in the queue. So what message queues provide is a exactly once semantic. So this is important for situations where there is some task that is being sent as a message. For example, if I say that execute this query or execute this script, so we want to ensure that no matter what, this is executed only once. We do not execute it twice. Because that can have unintended consequences on our system. So that is what message queues allows us to do. They are not meant to handle a very huge volume of data. It's just a asynchronous way of communication that ensures only one or exactly once semantics. So an example of message queue is a very famous example of message queue is RabbitMQ. Now coming over to publisher subscriber model, what happens in a publisher subscriber model is that there are multiple producers and then there are multiple consumers. So when a producer produces a message, more often than not, it writes to a topic, a particular partition in a topic, and that message is committed on that particular partition. Then there can be different consumers who are working for different use cases, which can read that particular message. So for example, if there is a user registration call that a producer makes, that so and so user has registered to our website. This is their email ID and phone number. So this information is critical to two people or two organizations or two teams in the organization. One is sales and marketing, because now they would want to contact this person and try to sell them their products. And another one may be account management or access management. that that team wants to ensure that only the features that that particular user is allowed to see, they see only that features. So what we essentially want to do here is that we want to communicate the same message to multiple teams in the same organization. So that is where publisher subscriber model comes, that the producer produces the message and then forgets about it, and then there can be multiple consumers that can come and read that same message. So this is what is known as at least once semantics, where the expectation from the streaming platform, which in our case is Kafka, is that the message is committed to the disk and it will allow to be read at least once. It will not get lost before any one of the consumer has read the message. So that is the main difference between a publisher subscriber model and a message queue. That message queue allows exactly once semantic, whereas a pub subsystem allows to have a at least once semantics. So now let's move over to the architecture of Apache Kafka. So Apache Kafka on a very high level has 6 main components that we'll talk about, which are producers, consumers, Kafka brokers, topics, partitions, and zookeeper. So let us start by understanding what a producer is. So producer, I think, is very self-evident that someone who produces messages for the Kafka cluster is termed as a producer. So what producer's responsibility is to process the data that they are supposed to process, convert them into a form of an event, which is a message, and then send it to Kafka. The next component is consumers, which again is very self-explanatory, that Kafka consumers are entities which read the messages that has been created by producers. So consumer's responsibility is to read the message from Kafka and then process that message whatever they want to, and then move ahead and read the next message. So there can be several consumers consuming different type of data from the cluster, and the beauty of Kafka is, which we'll discuss in detail, is that each consumer knows from where it needs to consume the data. So that is what allows them to avoid duplicate processing of data, or basically does not mandate that any consumer has to start from the beginning. They know that from where they can start processing the data as soon as they come up. So this is about producers and consumers. So these are not the integral part of Kafka architecture. These are essentially clients for Kafka cluster, which use the Kafka cluster, the setup that is done to run Kafka. The next critical component of Kafka cluster is Kafka brokers. So a Kafka server is known as a broker. Broker is a bridge between producers and consumers. So if a producer wishes to write data to the cluster, it is sent to the brokers. And if a consumer wants to read data from the cluster, it requests the broker for that data. So all information lies within the brokers of the Kafka cluster. So they are very important, very critical part of the entire ecosystem. So the next component of Kafka cluster is zookeepers. So this was in the earlier version of Kafka. However, in latest version of Kafka, we do not have zookeepers. The activities of zookeeper, or whatever zookeeper used to do, is now being done by the brokers itself, and some of the brokers are sort of labeled as special brokers called the bootstrap brokers, which perform the same task of what zookeeper used to do in earlier versions of Kafka. So what I'll talk about as zookeeper, but we can simply replace them with bootstrap brokers, and the entire thing will also make sense. So a zookeeper or a bootstrap broker is used to store information about the Kafka cluster and details of the consumer clients. So it manages brokers by maintaining a list of them. It is basically doing some sort of a heartbeat check or live probe to ensure that all the brokers that are supposed to be part of the cluster are actually responding to its ping request, or whatever way it wants to set up that heartbeat checks, and wants to make sure that they are alive to serve requests for clients. Also, there is additional responsibility with Zookeeper of choosing the leader partitions. So this is something that we'll discuss when we talk about partitions. So there is a leader partition, and which partition gets to be the leader is something that is chosen by Zookeeper. And in any scenarios where a broker dies, or maybe a new topic is created, a new partition for that topic is added, so in all those scenarios, it is the responsibility of the Zookeeper or the bootstrap brokers to send notification to all the other brokers of Apache Kafka, so that they are also aware of these changes and can accordingly serve requests from clients. So this is we can sort of think of Zookeeper as a overarching entity which controls the working or facilitates smooth working of the entire Kafka cluster. So this is one critical component in Apache Kafka. So these were the hardware or physical components of Apache Kafka. Now let's talk about the logical components of Apache Kafka. So primarily there are just two high-level topics or high-level logical components that we'll discuss. The first one is topic. So topic is nothing but just a common name or a heading given to represent a similar type of data. So for example, in an organization, I can have a topic which represents X API request or X API response, right? So it is nothing but just to store the response or request of a particular API. We name that particular topic with that particular string. So it is nothing specific, nothing special. Topic does not hold any specific meaning in Apache Kafka. There can be multiple topics in a cluster, and each topic can have multiple different type of messages. Topic is essential for producers to produce message, and then for consumers to consume message. So it also allows them to make sure that whatever type of messages the producer is producing, we can ensure that the consumer is also consuming the same type of messages. Then the next logical component, a very important component is in Kafka is partitions. So every topic will have a predefined set of partitions that is configured while we are creating the topic. The data or the message is stored across these partitions, and every partition carrying a data has an offset value attached to it. So a data in a partition is written in a sequential manner. Although theoretically we can have a very large number of partitions, however they seldom add value to your application. So what I have seen in industry is maximum of 40 partitions is sufficient to process requests at a rate of maybe 10,000 requests per second or 15,000 requests per second. But yeah, obviously if we are going way beyond that, maybe to 100,000 requests per second, or what Kafka claims is that it can process 1 million records or requests per second. So might be you'll have more number of partitions that are required, but generally we can achieve our use case, or we can solve our problem with much smaller number of partitions. So every partition has a offset attached to it. So let us just do a simple recap. There is a topic that is created for producers and consumers to read through, and then there are a partition of a topic. So for example, if there is one topic, say account details, and I create 10 partitions. So all those 10 partitions will have different offsets. What data will be written to which partition is a policy, is a strategy that we can define. We can set it as round robin as well. So every new message is written to the next partition and it rotates among those 10 partitions. And then the consumers can read from any of these individual partition. So this is one of the key point in Apache Kafka, is that you are not limited by the number of consumers you can have. You can have as many consumers as you want, till the time the number of partitions is either greater than or equal to the number of consumers. So in our use case, if there are 10 partitions for a particular topic, then the maximum number of consumers we can have is 10, which will achieve maximum parallelism. And each consumer can consume from the respective partition it wants to consume from. And This setting also is not something that we have to do manually, that which consumer wants to read from which partition, although we can do that, but that Kafka takes care and will ensure that as you increase the number of consumers, they always read from different partitions. For example, if I want to have 11 consumers when I have 10 partitions, so then the 11th consumer will actually sit idle, because no two consumers can consume from the same partition, because that will actually break the semantics or the processing of data in Kafka. So you can have only one consumer reading from one partition, but you can have the number of consumers equal to the number of partitions. That gives you maximum parallelism. And in every partition there is an offset. So offset is nothing but it can be thought of as a linked list head, which basically indicates that at what point or till what point a consumer has read the messages. So as a consumer tries to read a message from a partition, maybe it reads at offset 10. So it will read offset 10, read the message present at offset 10, process that message, and then will tell the Kafka cluster that it has read till offset 10. So next time when it tries to read, it will read from offset 11. So this is something that the consumer stores this information in Apache Kafka itself, and basically allows the consumer to know that where till what point has the data been read. So in scenarios where consumer goes down or maybe comes up later, it can basically identify till what point it has read the data and can continue processing from that particular point onwards. Another important concept that we should talk about is leader partition and consumer groups. So let's first talk about consumer groups. So as we discussed that there can be multiple consumers that are reading from the same topic. So we can have all those consumers to be part of a consumer group, so that even if in a scenario where one of the consumer in the consumer group goes down, which was reading from a certain partition, then the other consumers that are part of the same group can actually take its responsibility and also read data from that partition. So for example, coming back to our use case where there are 10 partitions and 10 consumers, if we combine them or make them join the same consumer group, then if from those 10 consumers any one consumer goes down, then the responsibility of reading the partition that consumer was reading will be transferred to some other consumer. So in this way we will ensure that all the partitions are being read, and consumer availability does not hamper our ability to read the partition from that particular topic. So that is one use case of consumer group. And also second use case is that if there are multiple teams that are reading from the same topic, so they can have multiple different consumer groups and they can read that data from the Kafka topic. So that again enables reading of the message by different teams in the same organization and allow them to process the data individually. The second important concept is leader partition. So for every partition in a Kafka topic, we will have a leader partition that is elected by the zookeeper or the bootstrap servers. So the leader is the replica that will serve the request for all the clients. So in Kafka, the read is allowed only from the leader partition. And then there is something called as the follower partitions or the in-sync replicas. So follower partitions are the partitions which are not the leader. So they do not serve requests from the client or other brokers. What their only job is to be in sync with the leader partition. Now in a disaster scenario where the leader partition or the broker which is hosting the leader partition crashes because of some reason, then after that crash, what happens is that the controller initiates a new election cycle where the in-sync replicas are the candidates, and out of those in-sync replicas, one of the replica is now chosen as the leader partition, and that replica now serves the request for all the clients. So this is where the high availability or data redundancy, resiliency comes into play, that you'll always have multiple copies of the same data that you're writing although you'll only read and write from the same copy so that you do not have any consistency issues, but there will always be replicas that are in sync with the leader replica, so that in case of a crash they can take its position. Now in scenarios where the replicas are not in sync, they are out of sync because of some reason, maybe because of network congestion, they are not able to read the latest messages from the leader partition, then the system comes to a halt because the leader partition has crashed and you do not have any in-sync replica that can replace the leader partition without losing the data that was yet to be synced. So this is one case where you can have data a loss or data corruption because of a crash of a broken node. But more often than not, the replicas that are there are always in sync, and even in case of a leader failure or a broker failure, you can very easily elect a new partition to serve request, and this is generally is almost always transparent to the producers and consumers that something like this has happened. So in a normal scenario, this works pretty well, but yeah, theoretically there is a possibility that the replicas are not in sync and there is a loss of data. So this is how partitions and topics are described or divided in Kafka. So this was the overall architecture. We discussed about producers, we discussed about consumers, we discussed about brokers. We also discussed about zookeepers, or what presently is known as bootstrap brokers. And then we discussed about topics and partitions. So one side note or one good thing to know about Kafka is that many people think that we have a way of ordering messages in Kafka, but if your topic has more than one partition, Kafka does not allow total ordering. So what that means is that it will allow partial ordering, which means that in a particular partition, you can ensure that messages are read in a sequential manner with increasing timestamp or increasing whatever value you want to sort of read the data on. But if there are more than one partition, then total ordering will not be supported, meaning all the records that are written to all the partitions, if you try to read them in the order of their time, it is not possible in Kafka. So this is one important point to know before we start designing our use case for Apache Kafka. So yeah, that was the high level architecture of Kafka. Now let's talk about different use cases of Apache Kafka. So I'll not go into examples where Apache Kafka is being used because I think it is now fairly old. I think the first time it was launched was in 2011, so it is almost 12 years old now, and a lot of companies have adopted Apache Kafka to perform a variety of use cases. So what we'll talk about is two high level situations that can arise in any use case in any domain where use of Apache Kafka makes sense. So the first one is asynchronous read and write. So many a times we want to build applications where we want to avoid synchronous reads and writes. So what that means is, for example, you have an API that serves your request. Now you get an API request, you prepare a response for that, you send that response back to the client. At the same time, you have to do some bookkeeping of the request that you're serving. So you will probably have maybe a MySQL server or some another database in backend where you want to commit that you have served this particular request. Now these two are separate actions, right? Responding back to client and at the same time committing the message on your backend database are separate actions. So you don't want to do them in a synchronous fashion, that the response to the client should not depend whether you were able to successfully commit that message to the backend database at that particular point in time. This is where the asynchronous request response or asynchronous read write comes into picture, where what you can do is instead of committing it to the DB, you can just publish it or send it to Kafka, and then your consumers later can run and read this particular request and process in any way they want to process. So now you're not tied with whether your database is up or your database is responding to you or not, or whether you have any retries which might increase the response time before you are able to commit the message to a storage system. So all these situations are avoided given you have Apache Kafka in between. Another key concept of Apache Kafka is which allows you to do is back pressure. So what back pressure means is that more often than not, you will have a system of disparate technologies or multiple technologies interacting with each other to create a product. Now, there can be situations where one of your component is very highly performant, whereas other component is not that performant. So if your API is able to serve a request of 100 requests per second, but your database only supports 10 inserts or 10 writes per second, then you're actually limited by the worst performing component of your entire system. So this is something that we want to avoid. We don't want to limit ourselves because of some slow component, and that is what back pressure means. Which this basically means that when your producer capabilities or the speed at which your producers are producing messages, the consumers are not able to keep up to that speed, the backlog increases, and then there is a certain limit to which that backlog can increase, right? So back pressure is something that Apache Kafka allows you to solve for, because you can produce messages at a very high pace or very high speed for Apache Kafka, and then you can have multiple consumers in the backend running and trying to catch up to those producers. So that breathing space or that that bottleneck is removed if you place Apache Kafka in between. So that is why Apache Kafka finds a lot of use in reactive applications where you are building reactive systems, because it helps to handle potential bottlenecks very gracefully and prevents any resource from becoming overwhelmed, which in turn increases the resiliency of your entire application or entire product. So this is one of the most important use case apart from providing asynchronous reads and writes. So this is what Apache Kafka is all about. Now I'll just quickly go through some of the selling points that Kafka has, some of the facts that Kafka publishes, that it is able to process so and so request with so and so data. So let's go through that. I'll just move to my Confluent page and see if they have published any matrices for that. Yes, so here is the published metrics for Kafka. So high throughput, it supports a very high throughput capable of handling high velocity, high volume data. It can handle up to million of messages per second. So that is a very, very high number, more than most companies require, apart from big companies like Facebook and Google. High scalability, Kafka clusters can be set up to use 1,000 brokers, which increases its capacity to process trillions of messages per day, petabytes of data, and hundreds and thousands of partitions. So this is basically the upper limit, the maximum you can stretch the Kafka cluster. You can have thousands of brokers, you can have petabytes of data coming in, and still the Kafka cluster will not collapse. It will still process the data with the same performance. You can have very low latency applications built. You can achieve latencies as low as 2 milliseconds, which is phenomenal. I think no other pub subsystem is able to guarantee such low latencies. Why it is able to perform such with such low latency is also a topic of discussion, which basically talks about how durable messages actually are in Kafka, but that is something that maybe we can discuss sometime later. But yeah, it is able to give you a low latency of 2 milliseconds. It can also act as a permanent storage, because what we look for in a database is that it should be durable, reliable, and fault tolerant. And these three properties are actually supported by Apache Kafka also. But this should not be misconstrued as a database. A lot of people think that we can store it in Apache Kafka for an infinite amount of time and then retrieve it as and when we want to, but that is not the actual use case of Apache Kafka. And if you try to use in that sense, you will surely face many challenges and realize that it does not work the way that you expect it to work. So as a general industry standard, a message on Kafka should stay for about 7 days, not more than that. After 7 days, it should get purged. That is how the purge policy of Kafka should be set. So it is not meant for storage, but yes, it does provide all that you look for in a database. And the last point is high availability. You can extend clusters efficiently over availability zones over different geographical regions, so that your disaster recovery is covered, you are highly resilient, and in case of any catastrophic event at one particular geographical location, you do not suffer a complete outage of your offering. So that is also what Kafka supports. So these are the points that is mentioned as the salient points of Apache Kafka. And with this, I think we can end our discussion. So we discussed about what Kafka is, what is the difference between publisher subscriber model and a message queue. We then discussed about all the 6 components of the architecture of Apache Kafka, which make Apache Kafka. Then we talked about how partition offsets work and how multiple consumers can consume from multiple partition. Then we also talked about 2 use cases where Apache Kafka has proved to be very useful, which is the asynchronous read and writes and back pressure. And then finally, we discussed these salient points of Kafka. So thank you very much for listening to this. Hope you could find something useful for yourself in this podcast. If you want me to dive deep into any one of the component or any one of the topics, please let me know. I'll be happy to research and get back to you with another podcast about the same topic. Apart from that, thank you for listening and see you soon with another exciting topic. This is Shivam signing off.